Welcome to Aerodynamics class number 143, and in this podcast we'll be talking about underbody diffusers of road cars. We have mentioned in many other podcasts, as well as in our automotive aerodynamics series on YouTube, that car diffusers are very important. And the majority of a car's downforce is usually produced by the diffuser, so like 50% or more. And they do this very efficiently. So for example, if you were to have a diffuser, you can increase the downforce a lot without much of a drag penalty. But if you had a rear wing, for example, or any wing around the car, often the drag penalty you get with this increased downforce is quite bad. So diffusers are a very good way of increasing downforce of a car without getting like that drag penalty. So it's very important to understand how this works, this part of the car. But before we go further, let's go through what a diffuser is. And to do that, we're going to be looking at a paper called A Numerical Aerodynamic Analysis on the Effect of Rear Underbody Diffusers on Road Cars, and you can find this in the link in the description. So the diffuser is located at the back of the car in the underbody section. We have a picture here of a Porsche down here a little bit. We have an armored body here, for example, but also a Porsche, and we can see the diffuser here. For those of you watching this on YouTube and Spotify, you can see what I'm pointing to on our YouTube or Spotify. And if you just listen to this on Spotify, you can also watch the video as well. So this is the diffuser here, and there's a small inclination at the back of the car. So if you look at the rear wheels on any car really, and then you look back on the underbody, there'll be like this slight slant going upwards. That is the diffuser. And the reason why this part is so important is because it can make the car's underbody act very much like an expanding cross-sectional area. So if the car is quite low to the ground, or if the car features skirts on its sides, so this is like when you have these little panels coming down to the bottom, like to the ground, this prevents air from escaping from the underbody and prevents external air from entering. Then the volume of the air under the car is effectively isolated from the surroundings. This may not seem like a big deal until you start thinking about the underbody geometry. So let's say the cross-sectional area is a certain amount near the front of the car. That is to say that, let's say at the front of the wheels, we look at what the cross-sectional area under the car is, and we find it to be a certain amount, let's say 0.3 square meters. So from the left side of the car to the right side of the car, from the ground to the underbody start, that entire area there is 0.3 square meters. The air at this point will have a certain pressure. So from continuity and Bernoulli's equation, we know that if the air is incompressible, which it is at this, usually with cars, at this like velocity below, let's say, 300 kilometers per hour, any change in the cross-sectional area will have an effect on the pressure. In particular, if we reduce the cross-sectional area, then the velocity of the fluid must drop, which will result in a drop in pressure. If you're not familiar with continuity or Bernoulli's equation, check out two videos on our YouTube channel called Aero Fundamentals number 8 and Aero Fundamentals number 7, respectively, to learn more about these topics. But coming back to a car's underbody and how changing the cross-sectional area, and hence the pressure, affects the car. Well, if we reduce the car's distance to the ground, this reduces the pressure of the air in the underbody section, and that increases the downforce because the pressure on the car's roof is greater than on the underbody. So this results in a pressure difference, which results in a net force down on the car. That is the general theory. So let's look at how this idea applies to a car more closely. In figure 5, we see the pressure coefficient plotted for the underbody of a car, or an idealized underbody of a car, as we go from the front of the car to the rear. And there is a red line and a black line. The red line is for a flat underbody without a diffuser, and then the black line is for the exact same thing, but you have a diffuser now. So let's explain first what is happening with the red line. So at the front of the car, which in this case is an idealized armored body, we have it just here. If you don't know what an armored body is, by the way, listen to podcast 141 where we discuss what this is in quite a lot of detail. So at the front of this car, we have a high pressure coefficient of 1. So the air comes to the front and hits the front, and it has to decelerate. So the pressure coefficient goes to 1. As the air starts to flow under the car, it accelerates a lot, and the result is a drop in pressure. So just around this region here, the very bottom of the car, then like bottom nose, we get quite a reduction in the pressure coefficient. In this particular case, it's going down to minus 1.7. And that's why we see the red line dropping with the black line, which we'll get to in a second with the black line. Then as we progress towards the rear of the car, the pressure coefficient steadily rises until it reaches almost the pressure coefficient of 0. You can see here the red line is almost plateauing and asymptotically reaching 0. When it reaches 0, we say that the flow has fully recovered. This fully recovered means that the flow effectively matches the free stream flow pressure and speed. In reality, we can never really get a full recovery in anything really. even over a very aerodynamic design like an airfoil, because there are always losses, and that means that the flow will always be in a pressure deficit. There is some energy that is missing from the flow, unfortunately, and that is based on how draggy this object is, how efficient or how inefficient it is. But in this particular case, it isn't a huge deal to have even this little loss, because the entire underbody is producing a lot of downforce quite effectively. So, okay, we're getting a drag penalty, but we're getting pretty good downforce. So we're getting quite a good effect here. Now that is for the completely smooth underbody with no diffuser. Let's talk about what happens when we have a diffuser. And this is the black line in figure 5. So figure 5 corresponds to the black outline with the armored body here. So we can see that there's like this taper at the back. To begin with, the pressure coefficient mimics that of the red line, but at around where the front wheels are, the black line starts to deviate from the red line for the pressure coefficient here. We can see here it starts to deviate. In fact, the black line stays at a lower pressure coefficient than the red line, which tells us that at this point, the car with the diffuser is producing more downforce here. And the way we can tell this is, so anything below 0, we can effectively say is producing downforce. Anything above 0, we can kind of say that it's producing lift. That's not a hard and fast rule, but it's a general indication. It also depends on what the pressure on the roof is. But we're just going to say anything below 0 here, because it's generally a good assumption to make. So we can see here this black line, it's a lot more negative than the red line for much of the underbody. That indicates that there's a lot more area underneath the the 0 axis here. So that means that we get more downforce. So this deviation here that we see from the red line, this black line from the red line, is caused in effect by the diffuser, and as we hit the diffuser, we actually see a local minimum in the pressure coefficient before a sudden increase in the pressure coefficient and an almost full pressure recovery. So we see here, as we reach the diffuser, the pressure coefficient drops a lot and then it just bounces back up. There's a lot going on here, so let's walk through this. So this local minimum is called pumping or pressure pumping. We then get a rapid increase in the pressure coefficient because the diffuser is increasing the cross-sectional area in this underbody location. So we can see here, if we were to have a ground like just around here, and we were to have a cross-sectional plane coming through, as we go more and more up downstream and we get to like the diffuser more and more, the cross-sectional area increases. Because the cross-sectional area increases, the flow doesn't need to travel nearly as fast to go through this opening, because we have like this flow coming from the underbody. That mass flow rate stays constant. And again, if you don't know what mass flow rate is, check out the video Aero Fundamentals number 7 on our YouTube channel, and we'll explain it there. And so the flat mass flow rate is constant. As it comes through, the cross-sectional area increases. The mass flow rate still stays constant, and for that to be the case, the velocity must drop. If the velocity drops, the pressure increases, and that's why we get this jump in pressure at the back here. So ideally, we get a full pressure recovery, but in practice, again, it never happens. In practice, the better the diffuser is, the closer we will get to this free stream pressure. And the reason why it is important to match the free stream pressure is because if there's a lower pressure, then that means that some portion of the rear of the car is experiencing a lower pressure, and that is more drag. What we just went through here, again, assumes largely that the air enters the underbody section that no air enters the underbody section except for the front, and no air leaves except for the rear. So the sides are completely blocked off. In reality, this isn't always the case, but you can add different geometric features to fulfill this, such as skirts, which we'll go through in this podcast as well. So these skirts are just flaps that go down to the ground on the sides of the car, and that segregates the underbody section from the free stream flow, so no flow can really escape or enter. So this is the diffuser in a nutshell. Let's move on to what this podcast is going to go through and look at that. We're looking at the effect of underbody diffusers in greater detail on the road car aerodynamics. In particular, we'll be looking at different setups, including a regular diffuser with a 7-degree angle, which we have down here a little bit. Let's go down to their CAD. So this is the CAD models here. We have different diffuser setups. We also have skirts, which you can see on the sides here. They only extend a little bit. And we have something called a front diffuser, which is not very common at all. And this is effectively where at the front of the car, underneath the nose, the underbody has this big bit gouged out effectively. And it's done as nicely as possible, as smoothly as possible, but there's still quite a big gouge of volume missing from the underbody, and that is a front diffuser. So let's begin with the podcast, what they're going to be going through. So as I mentioned, figures 9, 10, and 11 show the CAD models that they're going to be investigating. Let's talk about their research method. They are using RANds in OpenFOAM, and OpenFOAM is a free CFD solver. Now, they are using steady state, which is good enough for a general understanding of these features. The good thing is that these features have quite a large effect on the flow, so even fairly inaccurate CFDs such as a steady state RAN solver will still give good insight. I would expect that the accuracy of this CFD setup will be about 5 to 10% of the real life results. Now, I should also note that they are not using real wheels or rims. So you can see in this CAD, they just have like pretty much like cylinders, just very stubby cylinders that they're using for the wheels. So there are no spokes, there are no tread features here. So this makes modeling these wheels much more easily. You can get away with something much more simpler like a rotating wall boundary condition to simulate the rotation of these wheels. So the researchers also used the SST-K Amiga terminus model, which I'm a big fan of, and that's good for this application. The domain that they used was pretty decent. The distance from the outlet to the rear of the car is decent, that's 8 lengths downstream. The top and sides are pretty good. The distance to the inlet is okay. You might argue that it's a little bit longer, that it should be a little bit longer than what we have here, but I think that it's acceptable, especially given that the other limitations on the CFD setup will limit its accuracy anyway. So one thing that is a little bit alarming though is the mesh was a little interesting because the average Y plus was 40. This is very high. For a steady state simulation, you won't have as many problems getting it to converge with this Y plus, but still it won't help with the accuracy. And just as a side note, if you were to ever switch to a transient CFD solver, then that Y plus should definitely be dropped. Otherwise, there is a good chance that the simulation will diverge. So using steady state is a good way of effectively being able to cut corners and not have to drop your Y plus as much. So I mentioned cutting corners in a facetious way. It's not really a good idea to do, but if you want to do, then that's, I guess, up to you. Anyway, so their grid convergence study in this work is definitely better than what we've seen in the last couple of podcasts, mainly because the difference in the number of cells between each refinement is a non-negligible number. So each refinement resulted in 50% more cells in the next level upwards. So the finest cell count was 6.7 million elements. The one below that had 50% less. The one below that had 50% less again. So they were unfortunately quite cryptic with the meaning of each of the values they reported. They have a table here of different values that they measured throughout the grid independent study. I'm not 100% sure what these refer to. Instead, they refer the reader to another paper for details, which isn't good practice because all of the relevant information should be contained in this paper for us to be able to understand whether the results are good or not. Going on a wild goose chase is never a good thing. So from what I can tell though, the difference in the drag coefficient between the medium and fine meshes is only 1.2%, this value here, which is pretty decent. This indicates that convergence has been reached, especially considering that we have a steady state simulation anyway. So for the boundary conditions, the inlet velocity was 25 meters per second, which is a pretty standard velocity to test the car at in terms of aerodynamics. And the researchers also noted that they selected this value so that they could use this data that they get from this research in conjunction with wind tunnel experiments in the future. They also simulated the ground with a 25 meter per second velocity, which is important because if you don't do that, then a boundary layer will form, which is not realistic. So when you're driving on the road, the car is moving obviously, and the road is stationary, and the air is stationary from a world's point of view, unless you have like gusts and that, etc. But the thing that is moving is the car. When you go to a wind tunnel, the thing that is moving is the air, not the car and not the ground. So there is a mismatch here. So what we need to do is somehow make the ground move at the same velocity as the air, because if you don't have that happening, the air is going along a fixed ground, and that results in a boundary layer, which we don't get in real life. In wind tunnels, we have a bunch of different systems we can use to get rid of the boundary layer. In CFD, it's a lot simpler than that. We just say, okay, the ground is moving at 25 meters per second, the same as the free stream velocity. Then Bob's your uncle, you don't have to worry about the boundary layer. And that's what they're doing here. So they also specified a rotating wheel boundary condition on the wheels, which just adds an additional rotating velocity to the surface of the wheels without anything rotating. The Reynolds number was 4 million. Interestingly, the mesh was 6.7 million cells, and they ran the simulation on a 12-core workstation with 32 gigabytes of RAM. So the reason why I say this is interesting is because, given their workstation, they could always have definitely increased the fidelity of their model, even possibly switch to transient, because with this workstation setup, they could go to 15 million cells and the solving time would still only be maybe 3 days. as it stands, the solving time for the simulation was probably an afternoon. That's about it. So this entire study, from CAD generation to CFD setup to CFD solving, would have only taken maybe 4 to 5 days, which is pretty damn good considering that you're getting an entire paper out of only like 4 or 5 days work, and then you might have like some writing, etc. So within a couple of weeks, you have like a paper done. That's a very efficient use of time, which, you know, even if you were to use your workstation to do a more accurate simulation, then you're only going to be maybe about 3 weeks in terms of like from having nothing to an entire paper. So I would have liked to see a better CFD setup here. Anyway, let's move on to the results. Now we're trying out a different podcast format. Actually, we'll be covering the entire paper in one podcast instead of splitting it over 2. We're doing that because I think it flows better instead of cutting it up. So this results in longer podcasts, which means we'll only do 1 podcast per week instead of 2. That means that we will cover the exact same amount of material each week, but hopefully it'll be in a better format. So you have one major podcast just to listen to and like understand everything together, and that way you can remember everything as well as we go along. Anyway, let's go on to the results and talk about the entire results in this podcast as well. So in table 3, we see the lift and drag coefficients and the lift drag ratio, also known as the efficiency E, of the car with different geometric setups. Without anything, the baseline car produces almost no lift. It's minus 0.05, which is probably within the error. The drag coefficient is 0.32. So as soon as you add the diffuser though, so this first column here, the lift coefficient plummets to minus 0.57, which is really good for handling and cornering. Interestingly, even though we get such an amazing increase in downforce, the drag coefficient is almost unaffected, with it only rising by 5 counts to 0.325. In other words, the drag coefficient only rose by 1.6%, even though the lift coefficient dramatically dropped, which is what I mentioned earlier with diffusers being incredibly good at producing downforce with almost no drag penalty. So the lift to drag ratio is minus 1.76 for this setup, which is pretty good. So let's talk about when we put the skirts onto the car. So as soon as we put the skirts onto the car, the lift coefficient drops even more to minus 0.887, which is really good. The drag coefficient is almost unaffected at 0.324. So this makes sense because the skirts sort of extend the car's underbody a little bit to the ground closer, which then segregates the flow under the underbody more from the free stream flow. With the skirts and the diffuser, the lift to drag ratio drops even further to minus 2.7, which is quite good. So interestingly, when the researchers added the front diffuser as well, so the front diffuser, skirts, and rear diffuser, both the lift coefficient and drag coefficient suffered, and the lift coefficient increased to minus 0.773, a negative effect of 14.7%, and the drag coefficient rose by 8 counts, which is a 2.5% increase. So the front diffuser was no good all round. I should note that this drag coefficient increase of 2.5% could just be error of CFD as well, considering the fidelity of the CFD model. So with this setup of the front diffuser, skirts, and rear diffuser, the lift to drag ratio drops to 2.3, which is it's 50% worse than if you just had the skirts and diffuser and no front diffuser. So let's look into the flow physics to get a better understanding as to why these effects occur. In figure 16, we see a cut plane longitudinally through the middle of the car with different geometric setups. So we have at the top just the baseline car, then B is with the diffuser, the rear diffuser, C is with the rear diffuser and the skirts, and D is with the front diffuser, skirts, and rear diffuser, so everything together. And we see the U velocity plotted on these planes, and we see these lines. These are called licks, or line integral contours for short. So licks are, you can do them in Star CCM Plus and OpenFOAM, and they're pretty cool because they show where the flow is going, and if you look closely, you can see different vortices and different patterns. So let me zoom in a little bit so we can see that a bit better. So here you can see like these vortex patterns and like these singularities forming, etc., around the car. That's the benefit of licks. So for the baseline car, let me center this. Okay, we can see this now. So for the baseline car without any other flow control devices, the licks show one large vortex just behind the bottom rear of the car. So just there where I zoomed in before. When the car is equipped with a diffuser, a rear diffuser I should say, then this vortex is still present, but it moves downstream. So you can see it moves down and up a little bit. The other two flow control devices, the skirt, so C, and the front diffuser D, don't change this vortex too much compared to just the diffuser B, but they do change the wake a little. For example, the front diffuser results in the wake shooting up a little more, which is quite surprising considering that the front of the diffuser, so the front diffuser, is all the way on the other end of the car, but it might simply be because the velocity or the flow under the car is faster, which feeds into the rear diffuser better. Strangely, if we look at the licks under the car for when it has the front diffuser, so this D pattern, this D figure, we can just see black. So I don't know why that is occurring and why this is occurring for this flow viz, but for some reason that's all we can see. And figure 17 shows more detailed views of the wake here. We can see that, like with D, it shoots up a bit more. The vortex moves backwards with the rear diffuser added compared to the baseline car. Let's move on to figure 18. So figure 18 shows the ISO contours of the Q criterion equal to 50,000 1 second squared, I should say, for the baseline car. While we don't have any other information about the other configurations, only the baseline car, this view does show us quite a good idea as to what's going on the general car in general. And in particular, there's one feature which we don't see too often. It's this vortex coming off the hood here. So if for those of you just listening to this on Spotify, if you imagine a regular car with a hood, or the bonnet, whatever you want to call it, and then on the sides of the hood where it meets the sides of the car, then there's just like this vortex pattern coming, this like vortex coming off each side and going all the way downstream. It's just like this small vortex that just extends the entire way, and it has quite a high Q criterion, obviously 1 on 50,000 seconds squared, and the velocity is quite high, so like 35 meters per second, so it's moving quite quickly too. This is quite rare to have on cars, but this one does have it. So moving on to the pressure distribution in figure 19, we clearly see that the rear diffuser lowers the pressure under the rear of the car. So we see here, let me zoom out a little bit here. Figure 19 has the cross-sectional plane straight through the middle of the car. And on the figure A, we see this is just the baseline car. And at the rear of it, we don't really see much of a blue section. It's like maybe minus 50, minus 75 pascals underneath there. For the figure 19B, which is the car with the rear diffuser now, the pressure has dropped to like minus 250, minus 300 pascals underneath there, so it's really dropped a lot, which indicates that there's more downforce being produced. And interestingly, none of the flow control devices affect the pressure over the roof, which tells us that the effects of these devices are a little more localized than what we might expect. So we can see here the roof pressure is pretty much the same over the windshield even, and over the rear even, like over the rear spoiler, it's very similar. So the top part of the car is kind of isolated from the bottom part of the car in this particular situation. This is not always the case with other cars. Sometimes the underbody does affect the pressure on top of a car, but for this particular car, that's not the case. So figure 19 gives us a clear look at the pressure distribution under the car, and strangely, the skirts have almost no effect. So if we look at figure 20C here, we see the pressure coefficient. It's a little bit different. Like you can see, okay, maybe behind the front wheels here, we can see there's a higher pressure, but the rest of the underbody is fairly similar to when we just had the diffuser. So at this particular situation, this particular cut plane, the skirts don't have much of an effect. And this is a little bit surprising because the effects of the skirt is to increase the Venturi effect. But for this car, I don't think they do that much. I mean, we did see an increase in the downforce, but this pressure plane here shows that it's definitely not coming from here. And I think it's because for this particular setup, let me go to figure 10 and 11 so we can see the CAD of this car. We see the skirts, they're quite small. So the idea of the skirt is that it extends almost completely to the bottom of the car, so like to the ground. And the reason why we want that is because the more it can extend to the ground, the more it segregates the flow under the body to the rest of the flow around the car. The higher the skirts are from the ground, the more the flow can come in. So that doesn't really help the Venturi effect. To have the Venturi effect occur, we need to really segregate the flow, so when we do expand the flow or contract it, then the flow can change pressure accordingly. If we, for example, if we were to drop the pressure of the flow, well, if we didn't have the flow segregated from the free stream flow, what's going to happen is more flow is just going to flow straight into that low pressure region, and it's going to mitigate that low pressure, so we're not going to get that downforce that we want. So by dropping the skirts all the way to the ground, we can maximize this Venturi effect, which we're not getting here. The skirts are quite small. So that's why I think that we don't get too much of a change in the pressure for this particular plane. We need to drop the skirts more to the ground. So moving on, the figure 21 shows the pressure coefficient along the rear half of the car's underbody with the various flow control devices. They all exhibit similar pressure coefficient trends. However, there is some waviness to the lines when any of the flow control devices are added. So we can see the red line is just the baseline car. Then as soon as we put like the front diffuser or baseline or Venturi diffuser, the front diffuser, this line just wiggles around a lot. So in particular, the skirts make the pressure coefficient bounce around near the front wheels, as we saw in the pressure distribution figures, that the skirts do change the pressure around the front wheels. But once we pass this point, it starts to straighten out a little bit and mimics more just the car with the rear diffuser. Even more extreme is the front diffuser's effect on the pressure coefficient. Literally along the entire rear half of the underbody, the pressure coefficient just wiggles up and down, showing just how much of an effect this upstream device has on the entire underbody. And that makes sense because if you have something upstream and then it mixes up the flow a lot and makes it go really weird, then that's going to affect how the rest of the underbody can manipulate the flow. So the front part of the car is very important. So figure 22 shows some cool vorticity plots in the cut plane, but unfortunately I don't know exactly where this cut plane is relative to the car. I can see a vortex which I think is from either the hood or from the A-pillar, this vortex here, in each one of these figures. But apart from that, there isn't too much to discern the exact location of this plane. Anyway, wherever this plane is exactly on the car, adding the rear diffuser, which is figure 22B here, definitely changes the underbody flow. You can see in this figure, let me zoom in a little bit here. You can see in this figure that in 22A, which is this left part here, there is no discernible vortex in this region in the underbody section here. At least there's like nothing really that strong. But for the other parts of this figure, so in figures B, C, and D, you can see now there's quite a strong vortex in this region, and let me zoom in, so here and here. So adding this underbody diffuser in the rear definitely changes the flow in this region, and some reason it increases the vorticity and introduces this vortex. So this indicates that maybe the diffuser hasn't been optimized yet, and this inefficiency occurs because of this non-optimization. So with that, my little aerodynamicist, we come to the end of this podcast. And if you liked it, make sure to hit the like button. And if you want to see more like this, hit the subscribe button. And if you want to make your experiments 2-4% more accurate, get yourself an atmosphere hawk. It's an instrument we make to make your measurements that much more accurate, because the density of air changes by 2-4% every day. And in fact, if you go into your wind tunnel in the morning and then do some experiments and come back after lunch, the density of air will have changed by that much. And it changes even more from day to day, week to week, month to month, and season to season. These changes are usually between 5% and 15%. If you have a 50% error in your experiments, then chances are that you can't find too much, and what you are finding is really more just to do with chance than reality. So the Atmosphere Hawk gets rid of that error for you, so you can have accurate data. It also makes it much easier to validate your CFD because the validation data you use is now accurate, and you can specify the exact same density in your CFD as you had in your wind tunnel. So get one of these instruments for yourself and make experiments better. You can find it in the link in the description. And if you want to get better at CFD and or theory, check out our courses in the link in the description. And I'll see you next podcast. Peace out, amigos.